Wow, and everybody's so quiet. This is amazing. Okay. Thank you, everyone. We are going to get started. My name, as you know, is Taariq Lewis. And for those of you who do not know me, I am the former founder of SF Bitcoin Devs with Andreas Antonopoulos, also the co-founder of SF Cryptocurrency Devs with Nelly Mensah, Val, and Robert Durst. Also founder of a Bitcoin company called Serica, which is no longer in existence, and now co-founder of a company called Promise. We are exploring post-quantum protocols in privacy, as well as on Mimblewimble. And so if you are mining or actively looking to mine in Grin, please say hello to me, because we're connected with a lot of mining companies and hosting companies that are looking to host miners very cheaply. So that's my plug for myself, so please see me, I'd love to help. But this is the most important panel of the day. There is not going to be another more important panel than my guest, because he has been a man of impact and a professor of awesome in cryptography at Stanford. We begged him to give us 30 minutes today to talk about post-quantum cryptography and how it may impact coins like Grin and other privacy tokens. So please welcome Professor Dan Boneh of Stanford University. Thank you, Dan.
Yeah.
All right. So Dan, we're going to ask Dan a bunch of questions. This is going to be pretty exciting. Thank you, Dan. So Dan, let's jump into it. Okay, let's get straight off. You can tell us, and we won't tell anybody here, it won't go beyond 4 or 5 walls. Did you or one of your students create Mimblewimble and Grin?
That's how you want to start.
That's how I want to start, yeah.
Okay. Well, first of all, I should say, so thank you. It's a pleasure to be here. Thanks for inviting me. I want to say first that I kind of love the area of blockchains as an area of research. It's an opportunity to deploy new cryptography. On the internet, it's kind of hard. It's become much, much harder to deploy new crypto schemes. In the blockchain world, as you know, it's a lot easier. So it's been a fun area. I love it. You know, we've been teaching a class in this area for a long time, over 3 years now. So hopefully you hire the developers that come out of our class.
How big is that class, by the way?
Yeah, the class had over 250 students last time,
Awesome.
And so it kind of grows with the price of the currencies.
That's right. Correlation.
You know, attendance fluctuates with the valuation. So yeah, it's a wonderful area to work in. So thanks, and I think I'm not going to answer your question.
Darn it. Okay, Igno. Okay, so interesting that Igno is here, and then you came quite quickly. All right, so let's talk about an exciting area of science, which is essentially quantum cryptography or quantum computing. And the question we have is, how long before quantum computing impacts Grin? And all cryptography that use ECDSA curves. And you can tell us a little bit more about what is quantum computing, how does it impact cryptography? Give us that overview.
Oh, sure, yeah, happy to do it. So I imagine most of you have heard of quantum computers. The idea is that rather than using classical physics, it uses superposition of particles, and it turns out you can do certain things more efficiently that you can't do with a classical computer. The primary examples are, of course, Shor's algorithm for factoring in discrete log, and Grover's algorithm that gives a quadratic speedup for search problems. Those are the two classic examples, although there are lots of other applications. The driving force for developing quantum computers is actually their ability to simulate physics. So if you are designing drugs or fertilizers or medicines or anything like that, you need to be able to simulate chemistry, and not surprisingly, these computers are very good at simulating chemistry. So hopefully that's the business reason to develop them. If there is no business reason to develop them, they will not be developed. So there has to be a reason why one would want to build them. So the next question is, how long before they impact the crypto that's used on blockchains, like ECDSA? And I think there's a calculation that I would like to take you through, which is very simple. Which is maybe optimistic, but let's imagine that Moore's law applied to quantum computers. Yeah. So we started with, a couple of years ago, we started with 5 superconducting qubits, then we went to 15, then we went to 30, and now we're at 90. If you kind of plot this graph, it's starting to look like a Moore's law-like growth in terms of number of qubits. It turns out when you look at implementing Shor's algorithm, the algorithm itself doesn't require many qubits. It requires about 10,000 qubits or so, but that's assuming you have pure, perfect qubits. What's being built is very far from pure and perfect, so you have to introduce error correction. Right. And error correction introduces a huge overhead over what's needed. So the estimates is that you need to break, to get to the point where you can break crypto, the estimate is you need about 100 million qubits because of the error correction.
Now, when we say qubits, so I know that we have qubits and logical qubits.
Yeah.
So how do they matter?
Yeah, so logical qubits would be the perfect qubits, the ones that behave, that basically don't introduce any noise and that they behave exactly like the algorithm wants them to behave. Mm-hmm. Physical qubits are ones that when you, you apply, well, these are called Hamiltonians. You apply, you kind of shine a laser at them or hit them with EM radiation. Right. They don't behave exactly the way you want them to. They introduce a little bit of noise, and that's where error correction is needed. So let's continue with the calculation. So so we kind of have a Moore's law effect in the number of qubits. We have to get to around 100 million to impact crypto. Interestingly, RSA requires more qubits to break than ECDSA because all the parameters in RSA are much bigger than with ECDSA. So let's stick with the ECDSA numbers. That's right. So that would take about 100 million qubits. So when you do Moore's law, so you do a log base 18 of 100 million, and you get log base 18 months of 100 million, and you get about 30 years. Yeah. So the timeline, if you assume these computers will develop at the rate that silicon computers develop, it's about 30 years. So there's still room to breathe. Yeah. You don't have to worry as is. The interesting thing is, most blockchains depend on crypto for signatures, but much of the rest of the world depends on crypto for encryption. Right. Now, if you're encrypting data today and that ciphertext gets recorded, in 30 years, if somebody builds a quantum computer, they can go back and decrypt things that you said today. So for encryption, there's actually already a good business case to start using what's called post-quantum crypto, which we'll talk about in a minute, already today. So your data today remains secure for 30, 50 years. You can imagine governments want to keep their data secure for a long time. Banks want to keep their data secure. So for encryption, there's already a need for that today. For signatures, there's less of a need because it's only in 30 years that someone can break your ECDSA keys if the estimate is correct. Right. And so you only need to start worrying about that as we actually start to get news of quantum computers reaching levels that can affect crypto. And
it's your view that there are no 5-letter organizations that have even reached further than the 30-year limit you're talking about?
Well, look, obviously we can only speculate about what 3 letters or 5-letter agencies are doing. I can say that this is, I guess, public information. There's in the, do you want me to use a mic? Oh, okay. Sure. In the Snowden revelations, there was actually an explicit discussion of quantum computing. So we know there is some investment happening inside certain agencies, but we have no clue how far they got.
Got it. All right, so let's continue this 6-hour conversation in the little time we have. Let's talk about post-quantum-based cryptography. So you talked about signatures.
Yes.
And so what are the post-quantum categories of signatures?
Yeah, that's a great topic. By the way, you're right. Literally, we could be here for 6 hours talking about what the impact of quantum computing is and what we do about it. So the crypto community has actually been very hard at work on defending against quantum computers. In particular, the question is, imagine you're facing an adversary that's equipped with a quantum computer. What do you do? Yeah, and the answer is you move to what's called post-quantum crypto. So what is post-quantum crypto? It's basically crypto that runs on a classical computer. So Alice and Bob and you guys will continue using classical computers. You don't have to use quantum computers. But the crypto that you use for encryption, for signatures, it will be secure even if the adversary is equipped with a quantum computer. That's post-quantum crypto. So the first thing we have to do is we have to identify a problem that's easy to compute on a classical computer, but hard, or at least a problem that a crypto system that can be computed on a classical computer, but breaking it would be difficult even for a quantum computer. Okay? Right. So the question is, what are those problems? And we have, for signature, in particular for signatures, we have 3 categories, and there are 3 classes of post-quantum signatures. So let's go through them one at a time. So the first one is what's called a hash-based signature. So this is where we use this traditional, SHA-256, nothing more than that. Right. So we all know and love SHA-256. A quantum computer is unlikely to affect SHA-256. If it does, all you have to do is move to SHA-384, and you're fine. So hash functions are perfectly fine. So these signatures are perfectly fine. Everybody believes that they're post-quantum secure. There's only one problem.
The problem is these signatures are really large. I think somebody mentioned Sphinx earlier in the day.
Yep, we saw Sphinx here.
So Sphinx is a multi-use signature scheme. Signature size is around 30 to 40 kilobytes.
Oh, hold on a second. A signature 30K?
30 to 40 kilobytes, yes.
That sounds big.
Remember, ACDSA signatures are 64 bytes. Not kilobytes,
right.
not 64 bytes.
Right.
These signatures are around 30 kilobytes. If you kind of shave the parameters a bit, you can get it. You can build a multi-use signature that's maybe a little shorter, but it's still going to be in the tens of kilobytes. So that's kind of unfortunate. So this is useful for things like software updates. Yeah. So if we want to send you software updates are so big anyhow. It doesn't matter if you put a 20 kilobyte signature there. That's just as good. For a blockchain, that would be a little different.
A little bit heavy.
A little heavy. That's right. So the next approach is what's called lattice-based systems. So lattice-based systems are based on hard problems on integer lattices. I'm sure, again, you've all heard of lattice-based systems. I'll tell you in one sentence what the hard problem is. I'll take you back to your linear algebra days.
Yeah.
Yeah. So you're trying to solve a system of linear equations, and let's say you have more variables than equations. So the system is underdefined. So there are many solutions to the equations. The signatures are based on the problem of not just finding a solution to a system of linear equations, but finding a solution that is also made up of only small numbers, what's called a low norm solution. Yeah, and that turns out to be a difficult problem. In particular, we don't even have a good quantum algorithm for that problem. Okay, so if you want to read about
right?
That's what, not yet.
Yeah.
That's actually a really good point.
That's
I mean,
right.
Absolutely. All these, in crypto, unfortunately, we can't prove that things are hard.
Right.
It's just a lot of smart people try to break them, and they can't.
Right.
So we assume that they're hard.
That's right.
But so here we have to assume that these problems are hard for a quantum computer. So that's the second approach. If you want to learn more about that assumption, it's called SIS. So you can look it up and see how that works. The third category, so by the way, I forgot to say, so with lattices, signatures are about a kilobyte. Yeah, maybe just a little under a kilobyte. So still, remember 64 bytes?
Yep.
We have to move to a kilobyte.
Right.
Still quite expensive for a blockchain. So that's kind of unfortunate. And the third category is what's called isogeny-based crypto. So this is traditional elliptic curve cryptography, just twisted on its head a little bit.
Okay.
And there, what happens is, by the way, I have to say, isogeny-based crypto, it's a beautiful, beautiful area. And if you understand the Diffie-Hellman protocol, there's a way to explain it literally in 3 sentences. The buzzword is instead of using groups, we're using group actions. That's kind of a one-line description of isogeny-based crypto. It turns out you can use that also to build signatures. Unfortunately, the best signature scheme we have from isogenies is called C-Sign. It's due to Stephen Galbraith in New Zealand and his team. And that signature is also around 10 kilobytes. So also, unfortunately, because we're using group actions and not groups, there's a little bit less structure. And as a result, we can't do ECDSA tricks, and the signatures get bigger as a result.
So just to confirm, though, in 30 years, every blockchain that is ECDSA based is going to have to move. So everybody's going to have a size problem.
Well, actually, that's exactly what I was going to thank you. That's the point I was going to make, which is really you guys should be looking at us cryptographers, and you guys should be complaining, right? This is like I think we're in a blocking progress on blockchains in that there's a clear need for a post-quantum signature that's secure and is comparable to ECDSA in size, 64 bytes. I can tell you, we've been working very hard on this. Every scheme that we try to come up with, we've been able to break so far. So this is not like we're sitting on our hands. Yeah, we are working hard. I view this as kind of a critical problem for the blockchain community.
Right.
You guys should be demanding from cryptographers to work harder on it. I can tell you that we've been working hard on it. It's just hard. Yeah, it's a hard problem to solve. So I've
Give up, run.
So I've been very optimistic about having short signatures for my isogenies, just because the structure is so similar to elliptic curves. Why can't we just get ECDSA to work on isogenies?
Right.
But there's like a really fundamental stumbling block that's making it difficult. So it doesn't work yet. And like I said, we've been trying. It's just everything we've tried, we've also been able to break.
Right. And we're going to need not just the signature size to be manageable. We also need signatures to have the features like we talked about multi-signature. We talked about other type of signature features. I mean, which of these post-quantum signature categories will give us those features that we've had before with ECDSA?
Yeah, that's a great question right there. So right, so maybe one thing you could ask about is verification time, right? So ECDSA is also very fast to verify.
That's right.
Could we have signatures that are as fast to verify? So, for example, hash-based signatures and lattice-based signatures, they're actually even faster to they're large, but they're faster to verify than ECDSA.
Right.
Yeah. So at least, your blockchains will be enormous, but at least your signatures will be fast to verify. Yeah. Isogeny so far, they have some benefits for key exchange. They provide short key exchange, but they're somewhat slower. So yeah, I agree. We're working hard on these problems.
Right.
And the goal is not just to have a short signature scheme, but we'd like to have fast verification, and of course we'd like to have all the wonderful properties like threshold signing, aggregation, and those are all fantastic research problems. And I promise you, we are working on this.
So you think Grin will be able to take advantage of those as we go forward? I mean,
Yes.
obviously it's a truism, a question, but I guess the question is, when we think of where we are with Grin, and 30 years from now, where we want to be with Grin, will it be that these features come to Grin? Will it be easy for these features to come to Grin, or will it require either hard forks, lots of massive changes based on where we are with Grin today?
Ah, I see. Yes, good question. Right. So you're asking basically. So first of all, imagine in 15 to 20 years I'm not saying that's the timeline. Hopefully we'll have an answer sooner.
Sure.
But imagine we solve the problem in that timeline. That's getting close to the 30-year mark, right? So I would say that 30 years is the mark you should be shooting for. Again, that's my personal estimate, with a grain of salt.
Yep.
Which would say that maybe on the internet for encryption, deployment needs to happen soon, because it takes on the internet a long time to deploy new crypto.
Yes.
On blockchains, it's easier to deploy new crypto because of hard forks. So it sounds like this is not something the community needs to worry about right now, but definitely 15 to 20 years from now, this is the time when you want to start thinking about moving more aggressively to post-quantum signatures. The hope is by then we'll have a solution.
Right.
Again, not only will we have a solution, the hope is that whoever finds a solution, well, hopefully it'll be our group, will not patent it,
Right.
but will make.
Wait, hold on a second. You mean they can patent it?
Ooh, yes.
Okay, so that's a risk. All right, well, let's jump ahead.
So please, if you find a solution, don't patent it.
Don't patent it. All right, let's talk about some cool ideas in post-quantum cryptography. Let's talk about post-quantum accumulators. Do we have those yet?
I see. Okay, great. So, I guess this is the quantum session. So we just talked about post-quantum, but this is a great way to introduce new ideas that are coming up.
Yes.
Right. So there are lots of things we'd like to that blockchains want to use that are not standard, not kind of standard internet crypto. Yeah, the kind of a regular, old style crypto. So accumulators are one of these wonderful things, right? So a Merkle tree is a type of accumulator, right? You can add a lot of elements to the accumulator, and later on you can very efficiently prove that you have that an element actually is on the accumulator.
Right.
Well, it turns out there are actually accumulators with better properties than Merkle trees. In fact, Benedict is going to talk about those later today.
That's right. He's going to have a session here.
So I won't steal Benedict's thunder, but maybe I will just say those are algebraic accumulators that have much more efficient proofs in some sense than Merkle trees.
Right.
So there are strong reasons to use those accumulators. Those accumulators are actually based on what are called groups of unknown order,
Right.
like the RSA group.
Yep.
And it turns out today those are not quantum secure. Yeah, so the best accumulators, the algebraic accumulators we have today, are not quantum secure.
Got it.
Merkle trees are quantum secure. The new accumulators that have extra properties are not.
Yep.
So this is a wonderful question. How do we build post-quantum secure accumulators?
Yep.
Yeah, that's a wonderful problem to work on. And again, where things are short and have all the properties that we get from the RSA accumulators. I'm going to jump the gun on the next question.
Go ahead.
Which is, you may have heard of a new primitive that's, again, been designed specifically for consensus. It's called a verifiable delay function, a VDF. So maybe you've heard of a beacon chain that's coming up. So that's all based on these VDFs.
Yep.
So a VDF, what it is a way for anyone to generate a puzzle. So a puzzle just appears, and then it takes a certain amount of time to solve the puzzle, even if you have a parallel computer.
Right.
Yeah, so you can have a miner with 10,000 machines. It's not going to help the miner speed up the time to solve the puzzle, but the miner is still going to take 10 minutes, say, if that's the bound. Turns out these VDFs are useful for consensus. And again, these VDFs are built from groups of unknown order, and all the groups of unknown order that we have today are actually, they're all quantum vulnerable.
That's right.
So it's another wonderful open problem. Again, this is why I love this field. There's so many hard open problems to work on. Can we build post-quantum secure VDFs? And the answer is today we don't know. We don't have an answer.
Yep.
But again, this is something that we're working on. and hopefully we'll solve that in the coming years.
You said a key word there, proof of work.
Yes.
And so let's come back to proof of work in Grin in a quantum world. Do quantum computers impact proof of work?
Again, excellent question. All right.
I got a lot of these, man.
Right. Okay. So proof of work. Right. Well, hopefully in 30 years we'll have moved away from proof of work.
That's right.
Yes.
Mhm.
Well, that's the hope. But suppose we don't. What?
Verified delay functions are a good substitute.
As part of a larger.
As part of a larger, that's right.
Proof of stake.
Yep.
system.
Yep.
Right. So proof of work, of course, is based on hashing, and it turns out that quantum computers, in principle, actually could impact proof of work as well, in the following sense. So there's this algorithm of Grover that gives you a quadratic speedup for any search problem. Quadratic speedup. So if today.
Wait. So when we say quadratic speedup, what's that
Yeah,
magnitude?
let me explain. So let's see. So today, if you want to solve a proof of work puzzle with difficulty 2 to the 70, it would take, classically, 2 to the 70 hashes to do it. So what we do is we throw a lot of computing power, a lot of parallel mining power, and we solve that in 10 minutes, but it's still 2 to the 70 work. It's just distributed over many computers.
Right.
Still 2 to the 70 work. In fact, there's a lower bound that you can prove on a classical computer. If you're going to solve a search problem of size 2 to the 70, a general search problem, it's going to take time 2 to the 70.
Right.
You can parallelize it. It's going to take overall time 2 to the 70. In a quantum computer, there's this, in the quantum world, there's this Grover's algorithm, which gives you the quadratic speedup, which means that really the time to solve the puzzle would be the square root of the search size, which means it would only take time 2 to the 35 to solve a proof of work puzzle. Think about that. 2 to the 35. 2 to the 35 on a regular computer at regular Intel processing speeds, it would be, what is it? It would be a few seconds.
Yep.
Yeah. So instead of having huge mining rigs, a single quantum computer running at Intel speeds would solve the proof of work puzzle in just a few seconds and would blow all the miners out of the water. So that's potentially the promise of Grover search. It turns out that actually is a bit misleading. And the reason it's misleading is because we don't have perfect qubits, we have noisy qubits.
Right.
So you have to add error correction and all that. And it turns out when you do the calculation with error corrections, it's not as promising as it sounds. And we actually had to do this calculation recently for some study that I was a co-author on. And it turns out actually sort of the quantum computers that are being targeted will actually not impact proof of work. However, as the physics get better, as this is not an engineering problem, the better the engineering is, the less noise there is on the qubits, the closer you will get to the Grover bound, which means you'll get to 2 to the 35. The impact of that is actually quite fascinating. So suppose tomorrow somebody all of a sudden has a perfect quantum computer that can break proof of work in time 2 to the 35. What does that mean? What's going to happen? Well, we know what's going to happen. The hardness bound is just automatically going to adjust, say in the Bitcoin network, after 2 weeks. So what we'll see is basically a doubling of the difficulty,
right.
And then the proof of work system will go back to working properly. Of course, you could ask, if you have a quantum computer, would you really use it at full speed, or would you slow things down?
Right.
So lots of game theory questions you can ask there.
But if difficulty increases and there's only one machine that can go at that difficulty, doesn't that mean we have a problem?
Yes, but hopefully that's not how the world works, right?
Okay, all right.
If one organization develops a quantum computer, hopefully others will develop at the same time.
True.
And so we'll be back to decentralization. So the answer is proof of work can continue to work.
Sure.
You'll just see a massive adjustment in the difficulty rates. And in some sense, it's kind of cool because all of a sudden Bitmain is going to have to invest a lot of money.
Right.
In
Is that company still alive? Ooh.
Let's not go there.
All right. Okay. All right. So what are the resources that we as a community here, lots of awesome engineers, lots of folks interested in Grin, interested in cryptography, what can we do to learn more about the impact of quantum computers on cryptography?
Yeah, generally, the number one question you have to ask is, breaking crypto is not a reason to build a quantum computer. Yes, because we just moved to post-quantum crypto, and all your investment goes away.
That's right.
So that can't be the reason to build a quantum computer. There's got to be a business reason to build a quantum computer. And so I hinted at that a little bit in that it seems like computational chemistry
Yep.
is maybe the reason to do it. And the question is if whether that's a large enough market
Right.
for to sustain the massive investment that needs to happen. So far we have, there are a number of companies, IBM, Google, that are investing in the research into building quantum computers. Whether they'll sustain it for 30 years, it's an open question. We don't know. So if you want to learn more about that, I was just involved in a National Academy study about the viability of quantum computers. Should the U.S. government invest more resources in research into quantum computing? So the study just came out. So if you want, there's a book that's freely available from the National Academy of Engineering.
Yep.
Just look for Quantum National Academy of Engineering, and you'll find it. And it goes through all the use cases and the state of the art and the impact on crypto and what it would, why would you actually want to develop a quantum computer. So it's a good reference if you want to read it. If you want to learn more about the area, that's a good area.
Awesome.
To consult.
All right. Now let's take a little jump here from quantum to talk now about exciting cryptography primitives that you're working on. So tell us, what do you got in your goodie bag there? What else are you working on?
Okay, great. So I have to say, first of all, thank you for asking the question, in that we have set up this center called the Center for Blockchain Research at Stanford, and we love to work with the blockchain projects. So if you have good crypto questions for us, or even generally incentives and consensus and economic questions for us, please get in touch with me or any of the faculty in the center. This is what we're for. Yeah, we set the center so we can work with the projects. So questions keep coming up. I love talking to the various blockchain projects. Every project I talk to, I walk away with 3 new research problems to work on. In fact, bulletproofs came from a conversation that Andrew and I had a few years ago. So we love talking to the blockchain projects because of all these projects, because of all these research questions. So one project came to us recently with a beautiful question that has been completely solved, and I want to just tell you about it. This is the Handshake project, and they had this problem with airdrops. Yeah, so what they wanted to do was effectively airdrop to all GitHub developers. It's kind of a cool idea.
Yep.
Turns out GitHub developers have SSH keys, either RSA or ECDSA keys. Most of them are RSA keys. And GitHub makes those public keys public. Yeah, so you have a community of several 100,000 or maybe even millions of developers who have public keys. And when you want to do an airdrop, you can just airdrop to those public keys. So that's kind of a cool idea.
Look at that.
That's kind of a cool idea. So the developers just get the coins. What they were worried about is when a developer withdraws the funds from the airdrop, they don't want any stigma associated with that. So they'd like the developer to be able to withdraw the funds without revealing that actually happened. So how do you withdraw the funds without revealing that you're developer Dan who just withdrew the funds? So that's a beautiful question. So yeah, so we have a complete solution to this. So we call this a private airdrop.
Private
system.
airdrops, yeah.
This is actually being deployed in Handshake. Did they launch already, or they're launching? Or it's coming up. So this is being deployed.
Testnet 3 just came out.
Yeah, cool. And then the idea would be basically rather than airdropping to a public key, the airdrop actually is to a commitment to the public key. So you just see a list of commitments. You have no idea which. You can verify that the list corresponds to all public keys corresponding to GitHub. So it's a correct list of commitments. But then when someone wants to withdraw the funds, they just prove knowledge of the private key without revealing the actual key that's being used to withdraw the funds. Yeah, so we get a private airdrop system. And the beauty, this is why, again, I love the space so much. The beauty of this is Handshake is making all this available to anyone. So any project in the future who wants to implement a private airdrop could just use that system.
That's amazing.
And it's kind of a cool way to do airdrops from now on.
There you go. Wow, awesome. Thank you. And wow, private airdrops. Wait, how long did it take you guys to get to that solution?
Well, it was a couple of months, right? So it took some work.
Yeah, I mean, airdrops exist and now they're private. It's like they move so fast. All right, so last question of the day. You didn't create Mimblewimble and you didn't start Grin. I understand, that's fine. If you were, hypothetically speaking, to create a new cryptocurrency, Dan, what would you put in it?
What would I put in it?
Yeah, well, give us some features.
Like one of the cryptographic stuff?
Yeah.
Do you have another 6 hours? I think actually these guys are actually putting up.
Yeah, I think. Yeah, exactly.
This is a long conversation. Yeah,
all right, give us your top 3 features. You say, you know what? If I were doing this today, here's what I would put in.
Well, let's see. So signature aggregation.
Yes.
Yeah.
Yes.
No need to list all the signatures. If you can just compress them.
We could use BLS for that.
One. You got it. Let's see. Privacy via zero knowledge. Those are pretty cool mechanisms. What? And then
Bulletproofs?
and then for sure, yeah,
For sure.
yeah. And then efficient consensus.
Efficient consensus.
I think those are the.
What is efficient consensus?
So without burning a lot of energy. And
Right, verified delay functions.
oh, there you go.
There you go.
Yeah.
All right.
So like I said, this is a 6-hour conversation.
I know, right? We didn't have enough time. Okay. Well, thank you for the awesome answers and the awesome back and forth. Everyone, please give Dan Boneh a wonderful hand. I know John had a quick question to ask because he raised his hand, and since John is awesome, I want to give one question to John.
Remark more. Dan was right in saying that growth search algorithm applies to the hash cache proof of work, but Grin does not use hash cache. It uses an asymmetric proof of work cycle, which is quantum proof, fortunately.
Yeah, I was referring to the Bitcoin proof of work. You know, there are others. So you can imagine a space hard proof of work that would be much harder to implement in a quantum computer. So yeah, for sure, there are other ways to do.
Grin does have hash cache on top
That's right.
of the cycle.
Right.
The way it's implemented with the growing graph sizes, we actually keep the difficulty in the hash cache part from growing too far. So the advantage
Yeah.
of Grover on the hash cache part is always limited.
Yeah, I think that's actually a very good point. I was referring specifically to the Bitcoin proof of work. Your comment is exactly right. There are proofs of work that are already quantum resistant, in which case there would be no impact. My point was that even for the Bitcoin proof of work, it's not the end of proof of work. It's just that the hardness is going to have to scale up. So that